In the present session, we are going to discuss high frequency response of BJT amplifier. The objectives of this class is, first we have to discuss a Miller's theorem, Miller's duals theorem and high frequency response of BJT amplifier. Miller's theorem states that if that network consisting of n nodes, that is 1, 2, 3 up to n, then we have to take one of the node is reference as to be connected to the ground. If that a impedance or a resistance of a network is connecting between the any 2 points, for example, you have to consider 1 and 2, then this impedance is to be connecting between the 2 nodes. Then this is to be replaced with its equivalent impedance at the node 1 and the source and node 2 and the ground. Means here, if that anything is to be for this impedance is to be replaced with its equivalent volt impedances. This statement Miller's means this impedance is also known as a floating impedance. This simply impedance is known as a floating impedance. Means if you use that network solve or derive the networks with this floating impedance or a node, then that solution to that a circuit is more complex. To reduce the complexity of the network, then this impedance is to be replaced with its equivalent impedance at the input side and output side. Then that network is to be defined and set as, that means that node 1 that voltage is V1, at node 2 voltage is V2. Then this impedance is to be replaced with an input side is denoted with Z1 to the ground. This node N is grounded, and similarly that at the node 2 that impedance is to be replaced with Z2. The current flowing through this node is I1, current flowing at this node is I2. Then we need to determine that equivalent impedances Z1 and Z2 from this network. From this circuit, we can say that to find the node V1 and V2 that voltage. Now for this current, this voltage at this node is V1, voltage at this node is V2, potential at this node is 0. That current, because of this node 1, that current is to be driven current flowing through this is I1, and from the node V2 that current is leaves that node, this current is I2. Now we need to find the equivalent impedance according to Ohm's law, that a Z1 is equal to voltage at node 1 divided by the current leaves from the node I1 is I1. From this node, we have to determine Z1 is equal to V1 by I1. To determining this Z1, we have to applying a KCL to this node. Then we can say that current flowing through this I1 is defined as from the circuit diagram. I1 is defined as that V1 minus V2 by Z. Now we divide both sides by V1, then you are going to get this expression is to be defined as, if you divide this, you are going to get I1 by V1 is equal to 1 minus V2 by V1 by Z. According to Ohm's law, I1 by V1 is nothing but a 1 by Z1, this is equal to 1 minus AV by Z. In some of the textbooks, instead of AV, they use a standard notation that AV is to be defined as or named as K. Okay. For this, if from this equation it is clear that if you take this Z1, that input impedance is Z1 is equal to Z divided by 1 minus AV, where AV is equal to K is equal to V2 by V1, where V2 is the voltage at the node 2, it is an output node, and V1 is the voltage at the input, it is an input node. This ratio, output voltage by an input voltage, nothing but a voltage gain. Similarly, we need to calculate the what is the voltage or the impedance connecting between the node V2 and the ground. For this case, that impedance can be defined as once again at the output node, that Z2 is defined as V2 by I2. Now, this current I2 is the current leaves from the node 2. Find I2 from the circuit, then I2 equal to V2 minus V1 divided by Z. For this expression, divide both the sides by I2, V2, then I2 by V2 equal to 1 minus V1 by V2 by Z. This side, then this value that I2 by Z2 is nothing, I2 by V2 is nothing but 1 by Z2 is equal to 1 minus 1 by AV, because we know that AV is equal to V2 by V1, then this is by impedance Z. Hence, that Z2 is replaced with Z into Z divided by 1 minus 1 by AV. Means this circuit can be replaced with its equivalent impedances, then that problem will be solved in case of this is to be replaced with its equivalent value, then this circuit is simplified as, if your voltage applied between this point is V1, current is I1, then the impedance is to be connecting between this is Z1 is given by that expression, and similarly this is a terminal V2, this is Z2, and this is connecting between the ground. But in our theorem, you are interested only our frequency or high frequencies, that response is to be mainly depends on the capacitors. You have to determine a Miller's capacitance. A Miller's capacitance can be defined as, we know that Z is equal to R minus J X C, then Z1 is equal to R minus R1 divided by minus J X C1. This is Z. Then Z1 is given by, defined Z1 is equal to Z divided by 1 minus, Z into 1 minus AV. If you substitute this R Z divided by 1 minus AV, Z1 is equal to, comparing that you have to substitute an impedance, then you are going to get R1 minus J X C1 is equal to R minus J Xc divided by 1 minus AV. If you are comparing these two, that real component R1, compare the real and imaginary terms, then R is equal to, R1 is equal to R into 1 divided by 1 minus AV, and you are comparing that Xc1 is equal to Xc divided by 1 minus AV. but we know that Xc is equal to a reactance of a capacitor, that is given by 1 by 2 pi Fc. You are going to get this is 2 pi Fc1 is equal to 1 divided by 2 pi Fc into 1 minus Av. This 2 pi F cancels, then C1 is equal to C into 1 minus Av. In our textbook, standard book in Ballisted, they defined this C1 is defined as CMI. This means a Miller's input impedance at the input side. Similarly, if you define for the output circuit, we can define this is equal to Z2, that is R2 minus J X C2 is equal to R minus J X C divided by 1 minus 1 by Av. Compare that real and imaginary terms, then you are going to get our pure resistance. If it is a pure resistance, then you are going to get R divided by 1 minus Av. This is equal to R into Av divided by Av minus 1. Similarly, for this Xc2 is equal to Xc into 1 Xc into Av divided by Av minus 1. This is equal to 1 by 2 pi Fc2 is equal to 1 divided by 2 pi Fc into Av divided by Av minus 1. Cross multiply, then that C2, a Miller's effect impedance is given by C2 is equal to C into Av minus 1 divided by Av. This is also defined as Cm naught, where Cm naught is to be defined as a Miller's output impedance at the output terminal. Hence, we can replace a floating impedance with its equivalent impedances at the input side and output side, and they are given by these expressions. Next, let us consider the dual of the dual theorem. In a dual theorem, that is to be defined as if that impedance is connecting between the, means this is a network in any n input network, that impedance is connecting between the two nodes, then that input is to current is to be applied to the node 1, this current is to be node 2, this is voltage is V2, voltage at this point is V1, and current flowing through is I1, current flowing through this is I2. Then this impedance is to be replaced with its equivalent value. Therefore, we have to determine this current flowing through this is I1, sum of the two currents, that is nothing but I1 plus I2. To determine that equivalent impedance means, as per the definition, that Z1 is equal to V1 by I1 and Z2 is equal to V2 by I2. Hence, we can going to calculate the applying KVL to this point, then you are going to get V1 at the input side, that current voltage V1 equal to that Z into I1 plus I2. Divide both numerator and denominator by I1, then you are going to get V1 by I1 is equal to Z into 1 plus I2 by I1, where I2 by I1 is the minus current gain. Therefore, this is nothing but Z1 is equal to Z into 1 minus AI, where AI is equal to minus I2 by I1. Similarly, if you are applying KVL to this path, you are going to get V2 is equal to Z into I1 plus I2, then divide both the numerator sides by I2, then you are going to get I2 by V2 by I2 equal to Z into I1 by I2 minus 1. Therefore, you are going to get Z into Z2 is equal to Z into 1 by AI minus AI divided by, this is plus, minus 1 by AI plus 1. If you take this, then means this circuit is to be replaced with its equivalent value, means this circuit is to be replaced with its equivalent circuit, means in case of a dual theorem, this is given by this an impedance, then this nth node is connected to the ground, then there is an impedance is connected in series with the node 1, and here that impedance is connecting between the node 2, this is Z2 and then this is Z1 V1 I1. This Miller's theorem and its dual helps to solve a difficult problems. Next, consider the high frequency response of a transistor. We know that a transistor can be modeled by using the hybrid pi model. We have discussed these things in the first module. We know that because of that junction, there is a capacitance transistors at high frequencies. We know that there is a junction capacitance between this point is nothing but C, B, C, and there is a capacitance between this is C, B, E, and there is a capacitance between that is nothing but C, C, E. These are held responsible for the variation of the gain at high frequencies. If we consider the circuit of the high frequency response of an amplifier, if we consider this transistor, there is a resistance, a capacitor RE, CE, and VCC RC, then this there is a capacitor CC, then you have to connect RL, R1, R2, a capacitor CS, and then a resistance RS, this is VS is connecting the ground, R1, R2, RC, RE. This is a general amplifiers at the low frequency. At the high frequencies, there is a capacitance in between this exists, that capacitance is nothing but C, B dash, C, and then this capacitance is to be defined, there is a capacitance between these 2 points is defined as C, B dash, E, and then capacitance between this point is a C, C, E. These capacitors are responsible for this. Then this transistor is replaced with its equivalent model, hybrid pi model. This transistor can be replaced with, and also due to the wiring, there is a capacitance at the input side is known as CWI, and also due to the lead connection, there is a capacitance between this point is CW naught. These are the capacitors affect the gain at the high frequency. Now we have to replace these transistors with a high frequency hybrid model. We know that this is B, there is a resistance B dash, this is RBB, then this there is a resistance RB dash E, and also there is a capacitance in parallel with this is C B dash E. Okay. Now, and also due to this wiring capacitance, there is a capacitance at this point, this is C W I. this is at the between the B dash, and the similarly from the between the collector and a resistance, there is a due to the junction there is a resistance that is nothing but R B dash C, and there is a capacitor R, this is C B dash C, or the capacitance between the base and the collector. At the between the emitter and a collector, there is a, it is replaced with a constant voltage current source, that is Gm into V B dash E. This is in parallel with, there is a resistance R C E due to the a collector and a emitter junction, and there is a capacitance between these 2 points, this is nothing but C C E. This is the equivalent hybrid model of a transistor. Now, we connect the external components. To connecting an external components, then we need voltage at this, where V B dash is nothing but the voltage drop across this point. We have to transfer, then VCC is equal to 0, we have to transfer these values RC, R1, R2, RE into the circuit. We know that the at high frequencies, that reactance of a capacitor is almost 0, because this is equal, Xc is equal to 1 by 2 pi Fc. Fc is constant, as the F is approaches to the infinity or a higher, then that reactance is to be negligibly small. Therefore, that effect of this Cs, Cc and Ce at the high frequencies acting as a short circuit. Because of this is a short circuit, Re and Ce combination is acting as a short circuit. Therefore, that emitter resistance Re is grounded, that emitter is directly connected to the ground at the high frequencies. And other resistances R1, if you are looking into the input side, this R2 is already lies in between the base and a emitter, and R1 is to VCC grounded, means R1 is also connecting between the this point. That Cs is acting as a short circuit, this Rs is in series with Vs, and then it is grounded. And similarly, for the output side, this Cc is acting as a short circuit, then this values are connected to the Rc is replaced with equivalent circuit, and RL is connecting across this, and then you are taken output across this point. Means we drawn the transistor amplifier at high frequencies equivalent circuit. Because of this RB dash C and CBC dash, this effect is to be that in frequency, means the, because of this feedback between the base to the collector to the base, then this analysis of this complex circuit is becomes complex. To reduce the complexity, then you have to replace this combination, parallel combination to the input side and the output side by using a Miller's theorem. Then this circuit is to be equivalent circuit is, we know that already RB dash C is about 4 mega ohms at 1.3 milliamperes. Because of this high input impedance, input resistance, there is no current is to be flowing in this circuit. Instead of that current flowing to this, that current is to be always flowing through this path. Because of this reason, we neglect the open circuit resistance, we have neglected the effect of that resistance on the transistors at high frequency. Then this circuit is to be replaced with equivalent circuit is, we can redraw this. This resistance RBB is to be negligibly small when compared to that RB dash. Therefore, we can say that replace that B with B dash. Then you are going to get B, there is a resistance is RB dash E, and there is a capacitance, we can say that C B E, and the wired capacitance, that is a CWI, and then this capacitance is to be connected in parallel with that, this is nothing but CMI, where CMI is nothing but a Miller's input impedance, that is given by an expression CMI is equal to CBC into 1 minus AV. And similarly, this path at this resistance is also equal to this, then this is to be input and output are separate, then this is equal to Gm into VB dash E or VBE, then the resistance is RCE, and this we will take that all the resistances one side, you are going to get this is RC is in parallel with RL, and also this apart from this capacitor CCE there is a wiring capacitor Cw0, please here we have to make one more capacitance, that is Cw0, and this value at this point is C due to the Cw0, this is Cm0, where Cm0 is the Miller capacitance that is given by Cbc into AB, Cbc into R is equal, Rm is equal to R into 1 minus 1 by AB. This Cmo is equal to, I need to derive, this is equal to Xcm0 is equal to Xc into 1 minus 1 by AB, then 1 by 2 pi Fcmo0 is equal to 1 by 2 pi Cm C into Fc into 1 minus 1 by AB. This one cancels. Therefore, Cmo is equal to C divided by 1 minus 1 by AB. Means this capacitor Cmo0 and Cmi is to be calculated by using an expression, that this expression and this expression. Output is to be taken across, this is V0. Because if you observe that input and outputs are separate, there is no connection between these two, because this feedback is removed by using the Miller's effect of Miller's theorem. Now, this is to be driven by an external resistance, this is R2, R1, and there is an RS is in series with Vs. Now, we have to analyze these two circuits separately. This is to be replaced with its equivalent resistance at the input side, and then you have to replace this voltage drop across, this is nothing but VB dash E. For this we need to find, if you consider only this portion input side circuit, if you observe these two resistances R1, R2, means this is to be replaced with its equivalent value. That these CBE, CW and CMI are in parallel, then this circuit, that parallel combination is to be replaced with its equivalent impedance, that is capacitance, that is Ci is equal to CBE plus CWI plus CMI, and then this resistance is to be replaced with its equivalent resistance by determining the Thevenin's equivalent resistance. A Thevenin's equivalent resistance means that is nothing but the RTHI. When you are finding an RTHI, to find RTHI, a Thevenin's equivalent impedance resistance at the input side, you have to set Vs is equal to 0. Set Vs is equal to 0. When Vs is equal to 0, then this circuit is to be equivalent circuit is Rs is in parallel with R1, is in parallel with R2, is in parallel with RB dash E. This is also equal to, approximately equal to beta times Re. Then you are looking into this side, this is your RTHI, where RB dash E is equal to beta times Re from the small signal. Therefore, we can say that RTHI is equal to a parallel combination of, that is Rs is in parallel with R1, is in parallel with R2, is in parallel with beta times Re. Now, this circuit, that input circuit is to be replaced with its equivalent impedances. Equivalent impedances means this circuit is to be replaced with a Thevenin's equivalent model Vs is in series with RTHI, is in series with a capacitor Ci, and then your output is to be measured across this point is Vi. For this circuit, we need to find the ratio Vi by Vs. For this circuit, we are going to get, to determine Vi, Vi is equal to I into minus j x Ci. Therefore, that Vi is equal to that voltage Vs divided by total impedance R minus j x Ci. Substitute here, Vi is equal to I, you have to substitute the I value, that is nothing but Vs into minus jXci divided by R minus jXci. If you take this Vi ratio, Vi by Vs, this is equal to, and then divide both the numerator and denominator by minus jXci, then you are going to get 1 divided by 1 minus jXci into R Thi. If you calculating this, Xci is equal to 1 by, sorry, divide both the side numerator, this is equal to, sorry, R Thi divided by, if you divide by minus j, this becomes 1 minus jXci. Therefore, this is, if your Xci is equal to 1 by 2 pi Fc, therefore, you are going to get 1 minus j 2 pi f R Thi Ci. If you observe, this gain is a complex in quantity, therefore, we can calculate the magnitude and the phase. Their magnitude is to be nothing but a Vi by Vs is equal to 1 divided by square root of 1 plus 2 pi f R Thi Ci square, and phase of this is given by tan inverse of, because numerator phase is 0, denominator phase is minus tan inverse of minus theta, tan minus theta is minus tan theta, therefore, you are going to get a positive tan inverse of 2 pi f R Thi into Ci. Then this circuit transfers a maximum power if and only if that a Xci reactance is equal to a input resistance R Thi. To determining this R Thi, this frequency means all frequency, this reactance is not equal to the R Thi. For this point, therefore, we have to define at f is equal to Fhi, a particular frequency, means if your frequency is depends on frequency, if this function at the frequency at this frequency, then reactance is equal to R Thi, then we can say that this is equal to 1 by 2 pi f Hi into Ci is equal to Ri. Therefore, we can say that Fhi is equal to 1 by 2 pi a R Thi into Ci. This is the frequency. Then the gain at this frequency is given by, what is this frequency? What is the, how do you name it? Gain at this frequency is given by, you have to calculate Vi by Vs. If magnitude, if you consider this is equal to 1 divided by square root of 1, this is a reciprocal of this, therefore, you are going to get f divided by f Hi whole square. Now, we have to plot the frequency response of this gain versus a magnitude, then this frequency response, this f is in hertz or megahertz, this is a gain by Vi by Vs at the input side. At f is equal to 0, at f is equal to 0, this will becomes, f is equal to 0, the gain is becomes reciprocal is infinity, 0, therefore, gain is becomes, this is 0, this is equal to 1 by 1, that gain is to be remains constant. As the frequency increases, that response of the amplifier varies like this. For this case, at f is equal to Fhi, at f is equal to Fhi, then that magnitude Vi by Vs equal to 1 by 1, that is equal to 1 by root 2. This magnitude is 1 by root 2, means this is nothing but half power bandwidth, or 1 by 1 root 2, this is nothing but a 1 by root 2 times that mid by frequency gain. If you are converting into the decibels, then you are going to get at f is equal to Fhi, this is equal to minus 3 dB, gain is minus 3 dB. Therefore, it is known as, it is the upper bound, means that above that frequency, that gain of the amplifier is almost constant, below that frequency, gain of the amplifier decreases rapidly as the frequency increases. Therefore, it is known as Fhi is to be defined as upper 3 dB cutoff frequency, upper 3 dB cutoff frequency. For this, if you plot like this, then you are going to get. Now, we determine what is the effect of this at the output stage circuit. In the similar line, this is to be, when you looking into this, this is to be replaced with its equivalent circuit. For this output circuit, then what is the value of this output circuit at this point? For this circuit, we can say that when you are looking into this, these are all in parallel. Once again, from the output circuit, we can define a resistance, that is a C naught is equal to C CE plus C W naught plus C M naught. Now, this is a constant current source. Instead of a Thevenin's equivalent, we can determine the Norton's equivalent, a short circuited a load resistance. Therefore, these resistances are RL, means when GM we set this equivalent 0, then it is a open circuited, then you are going to get RC is in parallel with RC is in parallel with RL. Therefore, you are going to get this RTH naught, Thevenin's equivalent. To find the Thevenin's equivalent naught, you have to set a beta times, GM times VB dash E should be equal to 0. When this voltage current source is equal to 0, it is acting as open circuit, then RTH naught is defined as a parallel combination of RC with RL is in parallel with RC. Then this output circuit is to be replaced with its, we can define this is V dash, a current source, voltage source, this is RTH naught, and then this is C naught, where V dash is equal to a constant current source GM into VB dash E minus, because the direction is negative direction, therefore you can say the minus VM GM E dash into that a output impedance, Thevenin's equivalent impedance VH naught. If you follow the same procedure, this circuit is identical to the a circuit at the input side, we can replace, we can found a similar line, then you are going to get this frequency FH naught, means that is the upper minus 3 dB cutoff frequency at the output circuit is given by 1 by 2 pi R T H naught into C naught, and that ratio V naught by V dash magnitude is equal to 1 divided by square root of 1 plus F divided by FH naught whole square. These two. Now, this circuit analysis is to be replaced with this one circuit. If you are combining these two, you are going to get the two separate circuits at this and then this. Now, what is the effect on this of this FH naught 2 pi? And now, my question is, if FHI and FH naught are equal, these two are equal or different? If they are different, then what frequency component you are going to choose, upper cutoff frequency, either FHI or FH naught. From this relation, we know that FH naught is given by this and FHI given by this. If you observe that input impedance is to depends on that RTHI, if you assume this CWI and CC, because none of the frequency components are depends on that external component CC, CS and CE. It depends on only on the internally. Because of this reason, that input circuit is forward biased, therefore, that RTHI is smaller than RTH naught, because the reason is that output circuit is in parallel, one thing. Second thing is that input is forward biased, therefore, that CB dash E, it is a diffusion capacitance is greater than CC E, and also it is greater than CBC. These two also affect, because these two are coming to the picture at CM naught, but almost these two values CC and CB almost constant, but RTH is less than RTH naught, hence you are going to get FHI is always greater than FH naught. Then if you plot for the same frequency response, if at frequency is equal to 1, as the frequency varies, that frequency response is due to that frequency, because these as circuit components are differs, then you are going to get this frequency response may be like this. Then this frequency component is FH naught. Always for the to determine the bandwidth of an amplifier, always you have to choose either upper cutoff frequency, that is FHI and FH naught. Therefore, you have to choose this FHI for this circuit analysis. We derived an expression for the a frequency response of an amplifier, and then we found that a upper cutoff frequency is due to the input circuit and the output circuits, they are given by this expression. Now, we defined Cm I and Cm naught. For this circuit analysis, we found what is the effect on these values. In the previous class, we solved, for example, one problem. If you take the same example for this, now I am interested only in Cmi and Cm naught effect. In the previous case, we have taken R1 is equal to 40 kilo ohm, R2 is equal to 10 kilo ohm, RC is equal to 4K, and RL is equal to 2.2K. Okay. And we found that Re is about 15.76 ohms. Then what is the effect of this Cmi and Cm naught at the output circuit? We know that a Cmi is equal to Ci into 1 minus Ab, and Cm naught equal to Ci into C into 1 minus Ab minus 1. From this circuit, if you are not considering the external components R1 and R2, if you are looking into this side, that current is Re, and then we are looking output is taken across this point. From this circuit analysis, we count that Ab is equal to, means at mid frequency gain, we need to calculate that mid frequency gain is nothing but minus Rc is in parallel with RL divided by Re. For the, if you substitute this, you are going to get that Rc minus into Rc is 4 into 10 to the power of 3 is in parallel with RL is 2.2 into 10 to the power of 3 divided by 15.76. If you are simplifying this, you are going to get this gain is approximately equal to minus 90. If you substitute this equal to minus 90 in this expression, that Cm naught is equal to something called C into 1 divided by Ab minus 1. This is minus 1 by Ab is equal to minus, this is minus Ab plus 1, 1 minus Ab minus 1. Therefore, this value is to be approximately equal to C into 1 by 9 is 0.111. Therefore, you are going to get 0.011 minus 1. When compared to this one, this voltage gain Ab is much higher. Therefore, Ab is minus 90. If you consider magnitude, Ab is much greater than 1. Because of this, Ab is much greater than 1, that Cm naught is approximately equal to C. Okay. And similarly, Rm naught is approximately equal to R, but Cmi is 1 after calculating the gain of the amplifier. If you substitute, then this Cmi is equal to something about C into 91. This implies that capacitance at the input side increases due to the feedback capacitor or the junction capacitors between the C, B dash and C. Because of that reason, that FHI is also decreases, parallel combination. Therefore, you are calculating these values C into C times 91 times C. If that C of the CBC is a diffusion capacitance, this is about 3 picofarad. Therefore, you are going to get approximately 270 PF for the transistor currents. Okay. In the present session, we conclude that we are defined a statements of a Miller's theorem and a dual of its Miller's theorem, and also we derived an expression for the high frequency response of the transistor amplifier, and we defined that upper 3 dB cutoff frequencies FHI and FH0, and also how to solve that. I have taken simple example, and then I shown that how to calculate a CMI and CM0. In the next session, you have to take determine the short circuit current gain of the high frequency response, and also example on the high frequency response of BJT amplifier. Thank you.